I don't like calling it a standard. WiSUN specifies existing standards.
From EE Media, this is Moore's Lobby, where engineers gather to talk all about circuits. I'm Dave Finch. Today I'm joined by two people who are building the infrastructure of a young and emerging wireless connectivity protocol, WiSUN. Today we continue our series on wireless connectivity protocols for the Internet of Things. In our first installment, we talked about LoRaWAN, the long-range, low-power WAN nicely suited for industrial IoT and low data rate smart infrastructure. In this episode, we'll continue down the path of sub-gigahertz low data rate networking with an examination of WiSUN, a versatile connectivity specification that is considered to be the Wi-Fi of sub-gigahertz connectivity. We'll get fantastic technical insights from WiSUN Board Secretary Jeff Shebb.
The antenna is certainly a critical piece, and no matter what radio hardware you're using, no matter what protocol, if it's WiSUN or anything else, if you mess up the antenna, you're not going to have a very good radio.
But first, Peter Konazko is Director of Smart Energy and Smart Metering at Renesas. He's a professional engineer and member of the IEEE, and in a career spanning several decades, he's held positions at Mitsubishi Semiconductors, ST Microelectronics, Honeywell, GE, and most recently Renesas. Peter's here to share the industry context of WiSUN, how the specification has emerged, and where it might go next. So Peter, in the last episode, we looked at LoRaWAN. And here, LoRaWAN and WiSUN are two technologies designed for industrial applications. They're both sub-gigahertz, open, interoperable, secure, but they have their differences. So one is a star, one is mesh. They've got different underlying protocols. So from your perspective, how do these two protocols or standards compare with one another, and also with things like narrowband IoT and others?
Yeah, it is, I guess, agreed or accepted that a WiSUN network is more complex than a LoRa or a narrowband IoT network. I mean, the complexity of something like a narrowband IoT network is in the service provider. With LoRa, it is also an unlicensed private network. And so LoRa, because the data rates are lower, the applications that LoRa seems to be fitting in the best, smart meter is not going to be working on a LoRa network because the data rate requirements of these meters is much, much higher. WiSUN specifies up to 300 kilobits per second, and that can be scaled all the way down to 10 kilobits per second, depending on the quality of the link and all of that good stuff. I think LoRa has a similar adaptability. LoRa is a star topology, as you said, so you need an access point somewhere, multiple access points over the sort of geographic area of your network, and all of the nodes talk to one access point. So by its nature, a mesh network has the ability of nodes to talk through other nodes, and that in fact increases the range, sort of effective range of a WiSUN network compared to one that requires a node to have enough power and sort of line of sight visibility to the tower that is trying to connect to, where that is your limitation. Whereas with a mesh network, you can continue to talk through as many hops basically as you need to get to wherever the data is supposed to go. So your effective distance is multiplied because of the mesh network capability. Also, because you're 900 megahertz, WiSUN uses FSK, so frequency shift keying, as its modulation. So it's a very robust. It's basically a two-tone. One means zero and the other means one. So it's a very reliable air interface. Whereas LoRa uses a spread spectrum technology, chirp spread spectrum that has certain advantages. One of which is distance. But again, that distance is limited to whether the node can see the tower. So with WiSUN, you have the FSK modulation, but because it's a single carrier, you increase reliability and robustness because of the ability, as specified in the WiSUN specification, to frequency hop. So depending on your data rate, you have a certain number of channels, anywhere from a couple of digit, like 10 or 15 channels if your data rate is higher because you're using more bandwidth, to up to, I think, 128 channels in the US, to be able to choose from. So it's hard to jam. It's hard to interfere with because the channel hopping is done on a pseudo-random algorithm, and it's unknowable. So they approach, both LoRa and WiSUN kind of approach the same limitations, but from different ways of solving them, and that, I think, makes them applicable to different types of markets. So we like to think of not necessarily LoRa as competing against WiSUN or WiSUN competing against LoRa, or narrowband IoT, but more that by the nature of how they work, they're actually more applicable to certain types of markets than others. And we don't necessarily compete head to head that often. For things like flow meters, or metering that requires lower data rates or less data over time, LoRa can certainly, and does, and has carved out a space there. But for more data intensive applications, and also applications that need to scale to millions of nodes, WiSUN, just by its IP nature, we believe is more suited. And that's why it's basically targeted for the types of applications, sort of utility industrial applications, that it was originally designed to address.
So let's look at WiSUN a little more closely. This is an IP-based standard, of course. Is it strictly limited to smart utility applications?
So WiSUN, from its inception, always had a kind of a specific purpose, which was to address the utility market, utility communications market, the lower speed part of that market. So the interconnecting of smart meters and those kinds of assets. The U in SUN actually stands for utility, and WiSUN originally meant smart utility network. Since WiSUN was branded, the U has been changed from utility to ubiquitous. So it actually now stands for Smart Ubiquitous Network. And from its very beginning, it was conceived and designed to be an interoperable, reliable, and secure solution in the sub-gigahertz space, but also very much an analog for Wi-Fi. We like to position WiSUN as the Wi-Fi equivalent, so to speak, of the sub-gigahertz world. Mm-hmm. Certificate-based security, just like Wi-Fi, so EAP-TLS, so establishing the connection, deciding what node goes on the network, and what privileges it has. It's all completely analogous to how Wi-Fi does that. And it's also IP from end to end, just like Wi-Fi. So it's an IPv6 network. So if you're familiar with that, then you can understand the WiSUN specification very well. Because of the narrow bandwidth, that very large IPv6 packet has to be broken down to fit into smaller chunks to be sent successfully in the narrower bandwidth that exists in the 900 megahertz space. As part of the stack, there's 6LoWPAN, which is an ATF standard that performs that function of breaking down the IPv6 packet, and then, of course, building it back up for when it's received and move further on. Unlike LoRa, let's say there's no gateway, so there's no translation taking place. It's basically layer 3 at the UDP layer is where the specification stops, but you have basically IP from end to end, fully routable and meshable, and so that's really what it is. So the security is built in because of the certificate-based security that's implemented from the link layer basically up to UDP. The keys can be stored in the border router, so they can be stored basically in the radio itself, or they could be stored in the utility server. Basically, a AAA server, Radius server does the authentication, etc. So very analogous to getting on the internet, basically. The sub-gigahertz space is that we're talking about here is primarily 850 to 950 megahertz. So it's the ISM band, and it's an open band. It's a free band, a license-free band. And so WiSUN was targeted for that space. Why not 2.4 gigahertz instead? The advantages of the longer wavelength means that communication can go farther. The radio waves are less affected by obstacles like buildings and trees. And so for the types of environments where a network like that would be built, a utility environment which geographically and physically tend to be large, the sub-gigahertz space made sense for creating a specification for this kind of communication in that environment.
So if I think about the advantages of any protocol, and there's no one correct protocol for, smart anything really. It really
Sure.
depends on
Right.
having a self-healing, auto-optimizing network that is fully interoperable. I mean, it's just kind of a slam dunk, I would think, for certainly for utility, but not limiting it to utility. Like you said, this is really positioned nicely for the ubiquity of
Right.
of all these connected devices.
Yeah, absolutely. And we're seeing more and more adoption of WiSUN in those other spaces. So smart city, which is, of course, a very wide umbrella of applications. But within that, street lighting, parking, traffic and transport systems, infrastructure management or building automation, that kind of thing. WiSUN, the advantages of WiSUN in that sort of dense urban environment will work just as well as in a utility or something like an oil and gas environment or something where the geographically things are spread out quite a bit. In an urban environment, the advantages of the longer wavelength and of the self-healing quality of the network, et cetera, they're all applicable in these other types of networks as well. Smart home as well. We're seeing a lot of sort of hybrid solutions that start in that sort of smart home space. Everybody's trying to crack that market because everyone lives in a home of some kind. Mm-hmm. And so the market is huge for finally getting these kinds of IoT solutions into the home. And so what we're seeing is that companies that are addressing that market, they're kind of hedging their bets by putting on a board not just, let's say, LoRa, but they'll put down WiSUN, they'll put down LTE or narrowband IoT, plus Bluetooth and Wi-Fi. So
really, and populated on these boards too, not just like sockets.
Exactly.
Oh, wow.
Basically have them on there because the end user may need one or the other protocol, and it's hard to know in advance exactly what combination they're going to need. The other side to it that's equally as important is that, and we're very careful when we talk about, or I am anyway, when I talk about WiSUN, I don't like calling it a standard. WiSUN is a specification. And the reason it's important, the terminology there is important, is that WiSUN specifies existing standards. And these standards have been around forever. Even 802.15.4G itself, 6LoWPAN, IPv6, these are all, IEEE or IETF standards that they've been around and working in networks with millions of nodes, not just in the sub-gigahertz space, but in the internet, basically, for years and years. And they're all open. So there's nothing proprietary, there's no license fee, nothing like that. So if you buy a WiSUN certified radio, it could come from any vendor. And that's one point of contention with LoRa, where the radio is mainly available from one vendor. So there is some risk there. And it makes it, something that has to be considered by a designer. Do they take the risk of sort of a single supplier for such a network, or can they not take that risk? WiSUN takes that risk out of the equation because it's all open and anybody can have access to the specification and create a WiSUN solution and get certified.
I want to switch gears a little bit. And I also want to make it really clear, out of respect to our listeners, that, Renesas is not sponsoring this episode. This is not any kind of advertorial statement. So I'm in a tough spot because I have questions specifically about Renesas. I don't want to sound like I'm just out here, clanging the Renesas cymbals because, we're being sponsored or something like that. So with that being said, if I look at Renesas as a provider within this ecosystem, component solution and stack solution, how are you investing in this? What are you bringing to the ecosystem from your particular company?
We have designed 2 stacks. They're both certified by the WiSUN Alliance, both field area network stacks. And we license those, but they're free. The
Right.
stacks will only run on our microcontrollers. And that basically is our business model.
Mm-hmm.
Certainly, we have relationships with all of the large metering companies and all of the other WiSUN players, so they can build the radios with our chips. They can run our stacks that are certified. So our reference design will be, if it's implemented, as certified, it will interoperate with those other WiSUN certified products from Cisco and Landis, Nitron, and others. So that's kind of where we've positioned ourselves. We're the only semiconductor company that have a WiSUN certified stack. Our competitors have, because WiSUN is built on open standards, those standards are used in other stacks for other companies' microcontrollers. But as far as WiSUN certification, we're the only ones who have a WiSUN certified stack.
That's really interesting. I was not aware that Renesas was the only embedded provider out there that has the stack that's just ready to go off the shelf and licensed. And I think that's always a great way, whether you're a small or mid-cap company or even, an enormous corporation, global corporation. I think it's really important to be able to rapidly assess a given solution or approach to something with a known baseline that's, we'll say, 80% of the way to what you would need in your application. You just need to, build or fine tune or tweak above that. But to be able to have something you can drop in on your board. So I would imagine if this is the case, it would be a Renesas MCU, and then you'd have a radio chip, right? And you're kind of gluing those together. Or do you also have modules with the radio built in?
We try to cover kind of all the bases. So we first start with our own reference designs, and then so everything beyond that is kind of a replication of those reference designs. So whether it's a module manufacturer or someone who's implementing the communications in some other product, for the most part they'll take our reference design and go with it. We give the reference design away. It's freely available. So what a company can build on, we have 2 sets of solutions. So we have a high performance solution, which is adaptable more for the border router function of the spec. And we have a low power end node solution. So the high performance solution is a 32-bit microcontroller from our RX family, and a separate chip, which is the radio. And the silicon for the radio is our own. It's an FSK, transceiver, again, because it runs standards-based protocols. There's nothing proprietary about our radio, but it is our radio, and it is designed to work in the WiSUN space. We take that same radio, so the exact same silicon, and we put it in with a 16-bit micro into a single package for the low power solution, the one that is more targeted for the end node.
And that's
it's 2 chips in one package. One is the 16-bit micro, and one is the exact same radio as for the standalone high performance version.
Okay, and it is 16-bit, because I wondered if you kind of skipped over that, if there's an 8 and 32-bit jump that a lot of some companies make. But so now you've got 16-bit resolution, which, by the way, on these end devices, as you start to see the number of use cases expand and it truly becomes a smart, ubiquitous network, it makes a lot of sense to have as much precision, resolution, and horsepower as your battery will allow for, because meters are not just communicating power consumption and helping to aggregate up and seeing what the load, the demand situation is at any given point in a power grid, but they're also looking at things like power quality. And when you start doing mathematics, right, and all the transforms that are associated with that, it makes sense that you would want, a very low power microcontroller on there that also gives you the flexibility of a 16-bit architecture.
For sure. I mean, the meters are not just meters, as you said. They have come a long way, and in fact, architecturally, they're actually database. They're actually servers. So they actually an AMI network is actually a client server network,
Right.
where the client is the utility, going to the server of which is the meter and getting the information that it needs. And there's a whole sort of database structure within these meters based on DLMS COSEM, which is specifically a metering data protocol. It's an object-oriented structure, so you can have well over 100 objects that represent just about any kind of data type or action. They could be switching relays. They could be objects that just hold the serial number of the meter, pricing information, future and past and days pricing that are in there. So they're really quite sophisticated things, and they need to do a lot of things and store a lot of data and create a lot of data, like you said, like power quality. On the very high end meters, these are computers. I mean, these are 32-bit, very very fast devices in there. Maybe the radio has a 16-bit micro, but the actual number crunching there is quite intense for a small thing like that, and a thing that you wouldn't think is doing all of that processing. But now you can fit into one of these meters a functionality like power quality analysis that would not be possible, 10 years ago, let's say.
Right.
So as the devices get faster and the power consumption gets lower, the applications just multiply.
One thing that and this is a complete shift of gears on us, but one thing that our listeners typically respond favorably to is hearing from other engineers and other people in the electronics industry, just, especially somebody such as yourself. You started at ST Microelectronics. You mentioned that you had a particular focus at one point on ASICs and things like that. And then you were at GE Energy, which is huge. And
Right.
now essentially owning the connectivity space inside of Renesas, which is an enormous, just a legacy hero brand of the industry for a long time.
Sure.
As if there were a 5-minute answer to this, but when you look back on when you came out of college, say, and give yourself the first 12 months in the industry to where you are now, what were some of the things that pulled on you that sort of guided where your career went? Because some people will stay in the application lab and they'll be an application engineer for 45 years and then they'll retire. Some people go and veer off and do completely non-industry related things. But you've built this really cool career, and you've been able to have your hand in the technology the whole time, it seems.
That's a great question, and without sounding like it was all planned.
Right.
And that's part of it. You can only plan so much. You plan out your life so much. But what got me into engineering in the first place was that I was a hobbyist. I love radio. I love shortwave. I'm a ham operator. I'm a licensed ham.
Oh, nice.
Yeah, and so that was before I even knew there was such a thing as engineering. I built amplifiers. I was also into music, so built hi-fi kits and built my own projects from scratch. As I said, and
Cool.
So when it came time to decide, where am I going to go to school? It was almost an afterthought that it would be engineering. But then I quickly realized, well, I like this, so I should be an engineer. And that's what got me into engineering school. And when I graduated, I was very much an analog guy. And I graduated at a time where ASICs were still done by hand. Ethernet hadn't been invented yet. I mean, I was almost too early. If I was born 5 years later, I would have been in the cusp of what has become our industry, what has become electronics.
Oh, wow. Wow.
I kind of graduated when the analog world was starting to fade, but it was the world that I loved. It was, obviously there were computers at that time. It wasn't the Stone Age. And I had one of the very first, home computers. I had a TI 99-4A. Maybe some of your listeners will
those
recognize that.
The big plastic, was that the one with like the big plastic kind of shell, like the box on there?
It was, yeah, it had some sort of aluminum, cover as well to make it look bling.
Okay.
You plugged in the cartridges. It was supposed to be a competitor to the Commodore and the VIC 20, and it was very expensive. If you wanted to add on to it, the initial box was like $100, but if you wanted to add any peripherals, and TI thought that they would, kind of take over the home computing market with that beast. But I graduated right about that time when these things were still up in the air. There still wasn't, a PC. There still wasn't hardware description language to design chips. Everything was still being done by hand. So I worked in several companies, mostly focused on analog-y things. And then I actually dropped out a little bit out of the industry. I went back to school. I got a second degree in communication. I wanted to kind of broaden my horizons in terms of, understanding life and so on. I'd been living in a lab, it seemed, since I was a teen. Mm-hmm. And then I got back into the industry and the sales and marketing side, and I found that I really enjoyed that because it brought me back to the technology that I never stopped loving. And I was able to participate in it without being stuck in a lab. Not that being stuck in a lab is a terrible thing. I have lab equipment all around me here that I've acquired and still use, and I'm very sort of happy for the experience of knowing how to use it and getting back into it. But it's an industry that offers you these options, whether you know they exist or not.
Yeah.
You need to move within it. There are just so many things you can do. As I said, you can go from being in the design side, you can go from the hardware side more to the software side. There's so many resources today that didn't exist back then, tools that are so fantastic. Just a way of debugging an MCU today is just, if we had that, even 20 years ago, it would have been a miracle. The way that we're able to do things today. So the options are there. Yeah. So you can overplan, I guess, but you just kind of, it's a profession that allows you to follow your joy in a way, where if you find that after a while that software is really your thing, you can learn it. You can change your direction or your career focus and go into an area that is even more interesting to you than maybe the one you started in.
This episode is sponsored by Rode and Schwarz. Wireless devices and networks are commonplace, but the technology behind them is complex and sophisticated. Test and measurement solutions from Rode and Schwarz enable customers to quickly master this complexity. From new 5G technology standardizations to cellular and IoT product design and volume production, our unmatched portfolio enhances performance and reduces time to market. For more information, visit www.rode-schwarz.com.
Welcome back to the lobby. If WiSUN is anywhere on your radar as a design engineer, you'll want to hear this next conversation. Jeff Shebb is Director of Technical Solutions at Landis & Gyr, the largest global player in smart metering with one of the broadest portfolios in the industry. And Jeff just happens to serve on the WiSUN Alliance board. So who better to answer my technical questions about this emerging specification? Jeff, welcome to the lobby, and I know exactly where I want to start with this conversation. It's at the device level. So if I'm a device attempting to join a WiSUN network, what lies ahead for me? What will this involve?
First of all, the networks, WiSUN is based around a mesh network concept. So a little different from the star network that we think of with cellular or, traditional Wi-Fi and some other competing technologies. So when you're joining a network, obviously you need some network infrastructure in place, border routers, which are essentially the base station equivalent of a WiSUN network. You have to have a certificate that's installed in that WiSUN device. So that goes back to the security precautions and the security approach. But when it's powered up, it will essentially search for a WiSUN network in place. And it doesn't have to see a border router or base station directly. It can see one of its neighboring nodes. It's a peer-to-peer based communication protocol. So it will see that node kind of send out a solicitation to join the network. And at that point, you'll get this back and forth, handshaking and exchanging of security credentials in order to fully join the network.
I see. Okay.
The inherent architecture of WiSUN is such that, say you have, could be a building, an apartment complex, could be a neighborhood. Every device has multiple neighbors and multiple paths back to that border router and back to, a head-end system at the utility or enterprise. So, that provides robustness and reliability in terms of if a particular path goes down. The mesh is self-healing. You can find other ways to route back into that border router. It makes the network design and the deployment a little bit easier. RF conditions may change. Link quality to a particular neighbor, goes bad. A new building comes up or something like that. It's generally not a problem. The mesh is very robust and stable over time.
Right. So the mesh is robust. What about the actual physical RF performance?
The WiSUN protocol is operating as a frequency hopping spread spectrum system.
Okay.
So it's constantly hopping channels. So that alone gives you some immunity to RF noise and changing RF environmental conditions. But then on top of that, the routing protocol itself allows the node to seek out its best parent or best neighbor node. And so as conditions change and it sees its, success metrics to that parent deteriorate, it will kind of switch to, the next best parent or the new best parent, so to speak.
Yeah, that makes a lot of sense. And the more I learn about spread spectrum modulation, the more I'm starting to understand that it inherently offers its own security benefits.
Sure, absolutely. Yeah, if these devices as frequency hopping spread spectrum, every device is constantly changing channels. It's not tightly synchronized in WiSUN. It's actually an asynchronous system. So one radio is on one channel at a particular time. Its neighbor radio is on another channel. But each of these radios have to track where their neighbors are, what channel their neighbor is on at a given moment. So that if he has a message to pass on, he will hop to his neighbor's channel in order to transmit. From a security standpoint, one advantage is that makes it a little bit harder to sniff the network. You can't simply go onto one channel and observe the data being transacted between nodes because those channels are constantly changing. So that is a little bit of an inherent security advantage to frequency hopping systems. That being said, there are ways to hack it. There are ways to sniff it out and kind of piece things together, which is why it is critical to have on top of that, robust encryption and, mutual authentication before something can even join the network. So it's a multi-layer approach to security.
Switching gears just a little bit, or hopping to a new channel. What are some of the other verticals where you're seeing just no-brainer applications, like the perfect application of the technology?
One of the first ones we're seeing take off is smart street lighting. So that's kind of an easy growth off of utilities. In some cases, utilities may own or manage street lights. In other cases, a city does. But smart street lighting is an easy one. We're seeing other applications such as environmental and pollution sensors. I've seen gunshot detection applications, all kinds of different applications in a smart city that they can use to really understand what's going on at different infrastructure and assets throughout the city.
What are some of the silicon vendors, for instance, that you're seeing doing either a lot of heavy lifting or pretty exciting work in providing companies such as yours with the chipsets and the reference designs for this?
Yeah. And there's a good ecosystem out there to choose from some of the top, wireless silicon vendors. what you're seeing increasingly is you've got today modules that you can get, WiSUN modules, more system on chips being developed, and, have the MCU and compute power you need, as well as the RF transceiver. You're starting to see reference designs, but also software stacks, WiSUN stacks that can be licensed. So it makes it really easy, for a device manufacturer or vendor, someone who's got a sensor or some niche application to, get either a module or, increasingly a system on chip, and get a license, a WiSUN stack and get up and running quickly.
In your position as a director of technical solutions, just your own personal preference, your own opinion, when you look at the option of, well, we could go with a module and we could license a stack versus we could buy all the, the chips and do it ourselves and build our own stack. Does one look more attractive to you than the other, considering that A, you're an engineer and you love to solve problems and actually make things, but B, you have a sales and marketing team breathing down your neck saying, when's the next generation going to be released?
Yeah, absolutely. I'm torn. My background is developing hardware and RF design. But then I've moved into this, more customer-facing role and business-oriented role. And it's really a trade-off that you touched on, time to market versus cost, as well as, what are the core competencies of your organization? Do you have RF designers? Do you have embedded designers? Do you have some background in communications? Do you want to develop your own stack? Do you have that capability? Certainly for modules, if you're trying to get something out very quickly, time to market is important. Maybe you can take a little bit of a lower margin, or you can, bear more cost on your product. Then a module is the way to go. Kind of complete soup to nuts. Frequently, they can be pre-certified by WiSUN. You can have FCC certification. And in WiSUN, the end device still has to be certified. But if you're working with a pre-certified module, it greatly reduces the technical risk and the amount of testing and validation you have to do on your solution. So certainly that wins from a time to market standpoint. But, in our industry, Landis & Gyr, primarily, selling to utilities and, smart meters, you can get into the millions deployed. So you're also very cost sensitive. So that leads you to a more, traditional chipset based design, where you're maybe doing your own front end and, you're doing the embedded work and you're really optimizing the stack for your particular application. And, maybe you're running multiple applications out of your MCU. You've got your comm stack and other applications. So if you're doing, high volume product, very cost sensitive, absolutely, that's still the way to go. And that is still much easier these days with system on chips, coming into market, and the ability to license stacks if you want. But for quick and dirty, hard to beat a module.
Do you have firsthand experience with getting a product through that FCC certification for a wireless product?
Yes, absolutely. Like I said, going back into my history, I worked as a hardware and RF engineer. And it's true that, there's the temptation to not really worry about that until you reach the end of your design cycle and you're going to do validation. And then, potentially you have major problems that, delay you, and you have to respin prototypes and go back and fix things. So, you really have to, as a design engineer, you really have to have that at the forefront of your mind early on, know which of the, regulatory requirements that apply to you. Is it, FCC 15247, or is your product in another regulatory market, Japan, Europe, Australia, and just always follow that good, electrical and RF design practice, things like, grounding and, shielding, paying attention to things like that up front will generally save you a lot of headache on the back end.
Yes. Is RF hardware and especially PCB design, is that as much of a black magic sort of art meets science as it's purported to be?
I like to think so. It definitely used to be. In fairness, I think as you deal with modules and systems on chips, the RF geek part of me is like they're taking all the fun out of some of the RF design.
Right.
But it's still not completely idiot proof. And when you're taking these chips and even you have reference designs and you're putting them on the PCB, and you're having to do some layout, you're having to, understand where to put grounding vias, you're having to choose still, handfuls of passive components, resistors, capacitors, inductors. The antenna is certainly a critical piece, and no matter what radio hardware you're using, no matter what protocol, if it's WiSUN or anything else, if you mess up the antenna, you're not going to have a very good radio.
Yes. Oh man. So the reason I excused myself from any RF work was for this exact reason. You can do all the best things and still screw it up at the finish line. What are some common ways that engineers ruin a perfectly good design with their antenna design?
One of the easiest I've seen is, particularly here where, we have radios, but they're going in some other device. For us, those are smart meters. It could be some other kind of sensor. And so you have to think, where does this radio, is it on the same circuit board as, a lot of other power supply circuitry or digital circuitry? Is there noise that can be picked up at the antenna? Are there, electronics or mechanical features, conductors especially, that can distort the antenna pattern? What is the pattern you have in that device? What's the pattern you want to have? Is it a directional radio where I'm talking this way to a neighbor? Or in the case of a smart meter, you really want an omnidirectional pattern. It's a mesh network. You could be talking to multiple neighbors in different directions. Mm-hmm. So I think just, thinking about it, not just as I have this circuit card or this radio card or PCB that has an antenna and it's a great circuit board. That doesn't really necessarily help you when you're in a final product.
Right. Jeff, this has been really, really illuminating for me. And before we call it a day, is there anything that we didn't touch on that you would like to mention, or you think that would be helpful for anybody who's sort of exploring or trying to learn a little bit more about WiSUN and the different kind of long-range, low-power protocols?
Sure. The one thing we could touch on is kind of, where WiSUN is going. You mentioned kind of long range and, relatively lower data rate. When we talked about utility applications and some of the other applications, what we've been seeing for the past couple of years is that utilities have more and more data they want to send, aside from just reading a meter now or closing a switch. They want to really be able to understand the health and status of the power grid at different points. So that means more data and, potentially voltage waveform data, and transactions more frequently on the network. So that's really pushed us towards focusing on lower latency and higher data rates. So right now, I mentioned WiSUN launched its FAN certification program last year. We are in the process of finalizing a FAN 1.1 specification or release, which would maintain backwards compatibility with the existing FAN profile, FAN 1.0 we call it. But we're adding some extra features in there, including higher data rates using OFDM modulation, for instance. So I do think that's an interesting trend for the future is, kind of increasing bandwidth. We're talking about, supporting data rates up to 2.4 megabits per second. Certainly obviously not something you're going to be streaming, video or audio over, but much higher than, some historic 50 kilobit per second, data rate that we've seen in the past. There's definitely the desire to, push WiSUN in the direction of opening up more and more of those applications.
Another big thanks to our guests this week, Peter Kanazko and Jeff Shebb, who are kind enough to join us from their offices via Zoom to go deep into WiSUN. So what do you think about WiSUN? Does the fact that it's built on an IPv6 mesh make this more or less attractive for your application? Drop us a note in the comments on this episode on allaboutscircuits.com. And send me a note on LinkedIn to let us know what you'd like to hear about next. I'm personally kind of thinking narrowband IoT to round out this low data rate discussion, but we want to hear from you. And if you enjoy this podcast, please take a moment to leave us a review and to subscribe. It's a little gesture that goes a long way in helping us to build a meaningful community of listeners and contributors. Thanks for listening.